I'm your host, Michael Hiskey. I'm the Vice President of Marketing and Business Development for Kognitio, and I'm joined today by our Chief Technology Officer, Roger Gaskell, and honored to be joined by Dr. Phil Shelley, who's the CEO of MetaScale, and also the Chief Technology Officer of Sears Holdings. We're going to go through a quick opening and then hear remarks from Dr. Shelley, and then also some remarks from Roger Gaskell from Kognitio, do a quick summary, and then take your questions at the end. So without any further ado, I'd like to introduce Dr. Phil Shelley, the CEO of MetaScale and the CTO of Sears Holdings. Phil?
Maybe 30 seconds of background on MetaScale and why MetaScale exists and who we are. The history of us is 3 years or so ago we started on our journey with big data, especially in the Hadoop space. And as we started to get experience, we found that we were somewhat ahead of the market in the non-internet facing area. We were getting requests from people to help them get started with Hadoop and integrate Hadoop into an enterprise. So we were doing that on a voluntary basis, and after a while, we formed MetaScale to make that a commercial enterprise. So MetaScale is a subsidiary of Sears Holdings, one of the 33 subsidiaries. It's an IT services company focused mostly on big data and specifically Hadoop, and we are partnering with Kognitio in that respect. But first of all, the story here is mostly about Sears and how we got started in the Hadoop space. Sears, as you know, is a $43 billion enterprise. It's a large retailer with many thousands of stores, a large online presence, and mobile presence too. We have many loyalty members, tens of millions of loyalty members, where we capture a lot of data about those people. And we need to interact more and more intimately with those customers, market and campaign to them, give them better service, customized service. That was generating more and more data in our company. So we started, as you see on this slide now, with some real issues meeting production schedules. That could be production schedules on mainframes where we're doing batch processing. It could be it was on data warehouses too, where we have large amounts of overnight batch. We also had multiple copies of data. We have up to 20 copies of customer data, extensive ETL around the company. As you imagine a large company like this, it's more than a century old. We have many divisions that had copies of data, and they were using ETL copies that may be in itself an ETL copy from somewhere else. So our ETL landscape was large, no single point of truth, and the setup time and modification time for ETL was becoming very significant. Latency in the data, because of that ETL, was also significant, and we could have up to 4 weeks old data in some cases that was ETL copied in a long chain that would become almost unusable because of its age. So data latency was starting to be an issue, and our data warehouses, and we had several, were being really overconsumed, partly by ETL and partly by the workload. We could increase the size of data warehouses, of course, but they're very expensive, everyone knows, and we couldn't get a data warehouse big enough where we could keep everything in one place with all of the history. Mainframe workload was getting to be a problem, but we are on a mainframe elimination roadmap, and so we actually, of course, don't want to add mainframe capacity in the middle of that. We intend to remove mainframes from our landscape in the next couple of years, not add more, and so that was a problem too. And as everyone, I'm sure, knows, most people's IT budgets aren't growing, and ours aren't, but our data volume is growing very significantly. In some areas, it's doubling every year, and some areas a little less than that. But that was our problem, and that's where we started. So the next slide, please. So a little bit about Hadoop. You may be familiar with Hadoop. If you are, then bear with me. For those that are not, this chart tries to show you how traditional databases or data warehouses perform with large queries, complex analytical queries on different data sizes. As you see, most databases, as we know them, are very responsive with a few tens of gigs, maybe a few terabytes of data. We can get millisecond, microsecond, sometimes response time. Certainly seconds or minutes for large queries on small data sets is quite common on large data warehouses. However, when you get up into the hundreds of terabytes in your query, even the larger data warehouses can spend sometimes days. In fact, we had some that are weeks-long jobs that would run on very large statistical jobs on 100 terabyte size databases. That's starting to be not cost effective, of course, as well as nobody wants to wait 6 weeks for a result. So one of the use cases for us was doing marketing campaigning and individual coupon promotions for people. That's a heavy statistical job, and our marketing people wanted to do that weekly. When we first started, we could only do it quarterly on our data warehouse because the process was about 6 to 8 weeks long. How could we do it weekly, and how could we do it on a full data set rather than a partial data set? That's really why we started with Hadoop. As you can see, Hadoop doesn't do small queries well, and that is part of the reason that we're working closely with Kognitio here. The small, rapid queries and normal SQL is not a sweet spot at all for Hadoop. But that's why it's a red zone. It means it's inefficient. Once you get up to the 100 terabytes or more, or petabytes as we are, Hadoop really comes into its own with hundreds of data nodes, very large parallelism in the queries. We can consume, store, and query massive amounts of data very efficiently and extremely cost effectively. So it's this bottom end where the red zone of Hadoop is, where there is need for better tools. And that's what we're going to cover later in the seminar. If you go to the next slide. So that slide paints the picture of why an enterprise implementation for big data that includes Hadoop has to be an ecosystem. It's not just Hadoop. It needs other things around Hadoop to make it perform all of the duties that you will need in a normal enterprise. So let's go on to the next slide. So the integration of Hadoop into a large enterprise or any size medium to large enterprise requires considering quite a few things. First of all, the data source thing. How are we going to connect to our legacy systems? In our case, it could be data warehouses, it could be mainframe, it could be some DB2 or Oracle. We have all sorts of different sources, transactional systems that are more and more often now distributed, enterprise service buses. All of those things have to be connected to Hadoop. Now, those are quite readily done, actually. So once we know how to load and handle real-time or batch streams into Hadoop, and we've developed integration for that. But that is something that everyone has to consider when they use Hadoop. By the way, this story for us is Hadoop, almost entirely structured data, almost no unstructured data. You often hear people talk about Hadoop and unstructured data. Today in this webinar, we're really focused mostly on structured data, and that's the use case that we at Sears mostly use. The most important thing in my mind is an enterprise data model. How do you store and manage enterprise data in a single place? Now, it's cost effective to put it all in one place with Hadoop. We can keep it all in one place, all of the history, but the model, how you model that data becomes important. Not the schema, because we're not really worried about schemas in Hadoop like we would in a normal database. We flatten out the data, it's denormalized, and schemas don't really matter. But we do have to have a model. So what data means what? What is the single point of truth for the enterprise of customer or product or something else? And modeling that out early on is very important. And then ETL, as we know it, largely goes away. The fact you get the source data into Hadoop, single point of truth source at the most granular level, and then we transform it inside Hadoop. We don't copy it anywhere, we don't move it. Transform it into usable versions inside Hadoop. That pretty much eliminates ETL. Those transformations, by the way, this is not the subject of this webinar, but those transformations now we run in the order of 50 to 100 times faster in Hadoop than we would in normal ETL tools. So we have ETL jobs that used to run almost 20 hours a day that run in 15 minutes now on Hadoop. We don't move the data, we transform it and then consume it from Hadoop. And then the idea is that this enterprise data model is really driving reuse of data. Less latency, less copies, no ETL if possible. That really drives the possibility now of complete reuse, single point of truth of data. Hadoop's big enough to keep it all in one place. We can transform it into the right views, and we can reuse it all the time for everybody. So single point of truth really is possible now. It's economically very possible, much cheaper than it ever was with data warehouses, and that's a big focus for us at Sears. And then the next piece is where we're going to explore a little bit now with Kognitio is the data consumption and the user interaction. Hadoop's traditionally been a little difficult to interact with. For an average user, there are some tools now emerging, and we're going to talk about one today. Some tools now emerging that allow users to consume data from Hadoop in a simpler, more traditional way, but with some significant speed advantages. Hadoop brings the advantages of huge data storage, massive parallelism on the queries, but it doesn't allow that simple user interface that many tools are being built around. We really don't want to move the data out of Hadoop unless we have to. So we want to be able to use Hadoop to do the parallelism, to do the parallel queries, to do the heavy lifting, and only move it out when we have to. And so we're going to talk about that a little bit, or Roger is anyway. We do export data out to legacy systems where we have to. Of course, that's a duplicate of the data, and we really don't want to do that. And so it's something we really try not to do, but of course, in reality, you have to do some of that. And then speed considerations of loaders. How do we load data out of Hadoop into other tools? Roger's going to cover some of this because some of these data sets can be really large, and you want them to be large, but also you want to use Hadoop and the parallelism of Hadoop to truly crunch down the massive amount of data to smaller subsets. And that allows you to really focus on analyzing the pieces you really need in another tool and use Hadoop for whatever you possibly can. And so let's go on to the next slide. So really with Hadoop, we can cover this in the Q&A. I welcome your questions, by the way. So we have quite a bit of time for Q&A, and I'd love to answer anything you have. But you really have to rethink the way you store data. Enterprise data architecture, as I said, is important. How do you capture and store data? How do you structure it? Schemas, again, schemas don't really matter in Hadoop in the way they used to. The way you analyze the data and the way the cost of storage, the size of the data now is becoming pretty much irrelevant. You can keep almost as much as you want. It's not uncommon now to see Hadoop clusters over 50 petabytes. The way you analyze data is going to change. How you use the parallelizing function of Hadoop to query things. How do you bring data out? The speed at which you do it, the skills. And then the last bit is so critical is how users then interact with that data. And that's what Roger's going to explore now for a little while. So the learning for us is over the 3 years we've been doing the Hadoop Big Data exercise at Sears is really that we are ready for prime time. We're in heavy production with Hadoop in Sears, not just the internet-facing part of Sears, but the actual legacy large store-based company, which is by far the largest piece of our company, is heavily using Hadoop. We even do our SEC financial reporting on Hadoop now. So that's how confident we are. Data architecture is important. Workload management options here are significant. We really removed a lot of strain from our legacy systems. That could be enterprise data warehouses, mainframes, other batch systems. Significant cost reductions compared to those legacy systems. And then we can discover new opportunities in the data because now we have all the data in one place. We have all the history. We've recovered data from tape that used to be on tape. And so now we can have years of history on item in a supply chain or price history or anything we want all in one place. It's a big effort and shouldn't be underestimated. But the final thing I want to emphasize is it has to be part of an ecosystem. And in any large company, the way you load data, model it, the way you firewall Hadoop, secure it, the way you put data away, and then the way you interact with the data has to be an ecosystem. And there has to be a simple way to consume data. And one of the ways that makes it easy to consume data is the way Kognitio are now connecting with Hadoop. And Roger's going to cover that in some detail.
Okay, well, thank you very much, Phil. So I'm now going to try and explain how Kognitio and specifically in how in-memory systems in general try and plug some of the weaknesses of Hadoop. So from what Phil said, it's clear that Hadoop has many strengths. And I just want to really summarize what we believe those strengths to be, and then talk about the weaknesses and how Kognitio addressed those weaknesses. So Hadoop is obviously a very cost-effective platform. There are no license fees, and the platform is about as low cost as you can get, using commodity servers, local disk, standard networking, etc. But you have to offset this to some degree by the fact that there's a large amount of engineering and coding effort required to both implement and maintain a Hadoop solution, which is why companies like MetaScale have come into existence to help people with that complicated engineering bit. Obviously, once you've built your array of servers running Hadoop, you've actually aggregated together a very large amounts of processing power. So it stands to reason that you've actually got a very powerful data processing platform, and I think Phil mentioned several times that they were able to eliminate a lot of ETL processing and speed up a lot of ETL processing. So you end up with a platform which is both scalable and fault tolerant, but what you don't have is a high-performance interactive or ad hoc analytical platform. As Phil showed in his slide, when it comes down to the lower volumes of data, you don't get the sort of performance you need to allow you to do the train of thought analysis that your users are expecting when they do ad hoc queries. Being able to do complex processing with large data volumes in minutes, in several minutes, is fine for standard reporting and for processing data, but for ad hoc analysis you really need response times that are in the order of a few seconds, not response times that are in several minutes. There's several reasons why Hadoop is not very good for doing this sort of stuff. One of those is that it's inherently a fairly inefficient architecture, having been invented on the premise that unlimited processing power was always available. And that was true maybe for the likes of Google and Yahoo, but for us mere mortals, it's not generally the case. But secondly, and most importantly, the reason Hadoop is slow for this sort of thing is because the data always needs to be processed from and to disk-based data. So how does in-memory analytical platforms such as Kognitio solve these problems? So the slide here shows what we believe to be a reference architecture for a solution. So at the bottom of this slide, you have what we call your persistence layer. So you have your Hadoop infrastructure, although this could be other things, your existing enterprise data warehouse or a legacy system. And then on top of that, you put a powerful analytical layer, which is built from the same sort of hardware as your Hadoop cluster. But in this case, the hardware is configured with more CPU and more memory and less disk storage. This analytical layer, it holds the data in a traditional relational form, and therefore can be accessed via industry standard APIs using SQL, which most of the standard BI tools talk. And also, in the case of Kognitio, the data can be addressed using a language called MDX, which is the language taught by OLAP applications. So the same data can be addressed using tools that expect to talk SQL, as well as tools that expect to talk to pre-aggregated OLAP cubes. Except in this case, the cubes aren't pre-aggregated. The platform is fast enough to calculate all the results on the fly. The analytical layer is actually interfaces directly with the Hadoop cluster and sucks the data it needs directly out of the Hadoop system as it's required. There's no need to put an ETL layer or to put systems in place to actually move that data to. This is a tight integration where the analytical layer sees the data in the Hadoop system, the data that's made available to it by the Hadoop system administrators, and then can suck out what it needs. So I'd just like to explain a bit about what we mean by an in-memory analytical platform. An in-memory analytical platform is basically a DBMS, a database management system, where all of the data of interest or specific portions of the data have been permanently preloaded into memory. And by memory, I mean random access memory, the sort of memory that all computers have and all servers have as a standard basis. This is not a cache. It is very different to caching the most frequently used or the last used disk blocks. It's not a copy of a disk blocks. This is where data has been specifically loaded into memory in a format that takes advantage of the fact that this is a random access structure. The other key thing about it is the database knows at all times which data is in memory and which is not. And the optimizer can produce different query plans, can produce different ways of running a query depending on where the data is resident and where it isn't. The other key factor is that because the data is the database management system knows at all times which data is in memory and which isn't, it doesn't have to, every time it runs a specific piece of analytics, it doesn't have to ask the question, is this data cached or not cached? And that sounds like a simple question to ask, but it adds a lot of machine cycles to the inner loop of the query, which is running through your large data volumes. We don't have to have that code when we know the data is in memory, and therefore we reduce the inner loop of the query and we let things run faster, which is important when we're talking about very large data sets. The other thing important to say about an in-memory database is that by memory we do mean random access memory. We don't mean the silicon type memory that's used in solid-state disk drives and is designed to mimic the behavior of mechanical disks. It's a completely different order of magnitude performance level when you're using random access memory to fast SSDs. They're not the same thing, and the database has to treat SSDs as though they're mechanical disks, albeit fast mechanical disks. This description of an in-memory database pretty much fits with Gartner's latest description of an in-memory database. So if you'd like to do some background reading, there's an interesting article called The Who's Who in In-Memory DBMS from Gartner, which explains this in a bit more detail. So why is putting data in memory faster than having data on disk? Well, RAM is faster than disk. Well, really, that's only a part of the story. I mean, memory is just another place to actually store the data. It doesn't actually make a system fast. What makes it fast is the fact that analytics completely change the workload and characteristics on a database. Simple reporting and transactional processing is all about filtering the data of interest, i.e. get me the small amount of data I need to satisfy this particular query. Analytics, on the other hand, is all about complex crunching, and I'll explain what I mean by crunching in a minute, of the data once you've filtered it. It's the second step that becomes important, not the first step of filtering the data. And the filtered data can be large, because you're looking for patterns of behavior, large sections of data. You're not trying to get a few rows of interest. You're trying to find a pattern of behavior. And crunching needs processing power and consumes CPU cycles. You're doing difficult things in this case. So storing data on physical disks actually severely limits the rate at which the data can be provided to the CPUs. So you can only get a limited amount of data because of the speed of the disk up to your CPUs to do the crunching. So you can only have a small number of CPUs in the system. Whereas accessing data directly from memory allows as much CPU power to be deployed as you can afford to put there. So it really becomes a question of how much you can parallelize the platform. So what do I mean by crunching? Well, crunching is the operations which allows you to understand what's happening in your data. So when you're doing big table joins, when you're sorting data, when you're aggregating data, when you're grouping it, when you're doing complex analytical functions against that data, it becomes very much CPU bound. An example of this is we do a lot of work in the retail analytics space, and when people are doing basket analysis, understanding people's buying patterns, i.e. what do they buy with when they buy one product, what do they buy with it, you end up doing what's called a self-join, where you join a huge fact table back on itself. And if you've got a 50 billion row fact table and you join it back on itself, you actually end up doing 2.5 times 10 to the 21 individual join operations. So you can see that uses a lot of CPU cycles. So complex operations like this are CPU bound, and assuming the system is not disk I/O bound, i.e. in an in-memory system, they become CPU bound. So for analytics, the CPU is king. And the market really needs to come up with a new metric for how we measure the ability of a platform to do stuff with the data as opposed to the current metrics, which are really about storing data. And one metric we use here at Kognitio is what we call the gigabytes of data per CPU core ratio, or the core data ratio. And we would suggest that this is a fairly rough but reasonable method of trying to work out a system's ability to actually do analytics. And we here at Kognitio would argue to do this sort of stuff effectively, you really need ratios where you have less than 10 gigabytes of data per CPU core. This measure is somewhat crude in that it does not take into account how efficiently a platform can utilize the cores available to it. Now that we are CPU bound, we need to treat each CPU cycle as precious. And a high-performance analytical platform will use techniques to make sure that every cycle is efficiently used. And Kognitio, for example, uses a technique called dynamic machine code generation to turn all the query steps down into the lowest, simplest form, which is actually machine code. One thing you need to be aware about in an analytical system, in an in-memory system, is where you've effectively now used all of your CPU power efficiently to actually run the queries, to run the analytics. The act of compression has a different effect. When a disk-based system, compressing the data allows you to read more data per disk access and make the database go faster. In an in-memory system which efficiently utilizes all the machine cycles to run the query, compressing the data makes an in-memory database go slower. And I don't think this is something that people have really started to realize yet. It's something that will become apparent as in-memory systems become more and more prevalent. So to summarize the requirements of in-memory analytical layer, true parallelization. It needs to be able to fully parallelize all operations, scaling both up and down. A single server or small server cluster simply cannot hack it when it comes to big data. Moore's law says that the power of processing doubles every 2 years, and this still remains true, but data volumes are doubling every year. So we have to be able to scale out. We have to be able to combine the power of many individual servers, every single core in all of those servers, and we have to be able to make every query run across all of the cores equally. Every CPU core is equally involved in every single query. So the Kognitio Analytical Platform, we've added a number of features in version 8, which is our recent release, that support this analytical layer approach. So in V8, we have introduced a feature we call external tables. And external tables allows data that's held on disk in other systems other than Kognitio, systems such as Hadoop, can be seen by the user of the Kognitio system as non-memory resident tables. The users can then select those tables and suck them into memory. So they simply say, this is the data I want to bring it into memory. They can bring all of the data into memory, or they can bring portions of the data into memory by specifying which parameters they want to use to filter the data. Kognitio system then goes to the Hadoop system and seamlessly sucks that data out of the source system into Kognitio memory. And it's all managed by SQL or tools that generate SQL, such as our management GUI tool. So there's no interaction by the user with the Hadoop cluster. So the Hadoop administrator creates data sets, as Phil was talking about. They have created data sets from the raw data. They've presented those data sets to the Kognitio system, and then the Kognitio user can then choose which data to suck into memory within the Kognitio system. And that data will stay in memory until the user specifically tells the system to drop the data. This whole sucking process is designed to be very, very fast. We've gone for a very tight integration so that we can make this a very high-speed process. There's no point in producing a system where you can suck terabytes of data out of your Hadoop system into memory in in-memory analytical platform if it takes many hours to do it. It has to be very high performance. So we've gone for a solution that sets up multiple parallel load streams. Every Hadoop node can stream data up to every Kognitio analytical platform node, and we can demonstrate on moderately sized systems, we can demonstrate load rates in the multiple tens of terabytes an hour. We have two types of connector to allow for different types of connectivity into Hadoop system. So we have the simplest connector, which connects directly to HDFS files. So it can see files in the HDFS file system, and the user can then select files. They see them as tables, where each file is a table, and can pull the whole of that file into memory. So the whole of the file comes up. Obviously, the data if the data by the Hadoop administrator has been split into files on some basis, then they can select different portions of data, but the whole of the file is loaded. The more complex connector that we have is the filter agent connector, and in this case, what happens is that we actually download a filter, an agent that we produced. Wrapped in MapReduce down to every node in the Hadoop cluster. And when we then go to Hadoop and say, give us some data, we can actually filter the data from the file and just bring up the data of interest. So for example, if a file contains 5 years of transactional data and the user is only interested in what happened in the last 6 months, he can say to the Kognitio system, this is the data I want, but I'm only interested in the last 6 months, and I'm only interested in these particular columns within that data. And Kognitio will pass those parameters down to the Hadoop cluster, and the Hadoop cluster will do the filtering, so that we will only bring up the data of interest into memory within the Kognitio system. So in this scenario, we're allowing Hadoop to do what it's good at, which is filtering data, and the analytical platform is doing what it's good at, which is the complex crunching of the data using all the CPU power that's available to it. So I just want to talk about another feature which is not specifically aimed at Hadoop, but is builds on this analytical platform idea that comes out with Kognitio version 8. And that's the ability to embed external scripts into an SQL query. So we can actually run third-party scripts embedded in an SQL wrapper. Those scripts could be Perl, Python, Java, the R libraries, SAS scripts, anything that's executable on the servers that Kognitio is running on, we can actually call out to those scripts. And it's a one-to-many rows in, zero-to-many rows out mechanism, API, so that you can select some data using your SQL query, you can send it to an external script, and you can get some data back. And this is basically extends the ability to do stuff that would be difficult in SQL, allows routines to be written in all different languages and different scripting languages to be able to do more complex stuff. So this particular example here has some Perl embedded in SQL query, and you can read at the side basically what it is. But it's just an example of the sort of things you can do to extend the power of SQL using external scripting capabilities. So what sort of hardware requirements does a Kognitio in-memory platform require? Well, it's the same sort of industry standard servers that you use for Hadoop. You probably choose to configure the servers with more memory and maybe more CPU cores because that's what dictates the performance of the system. But it's fundamentally the same servers with the same type of networking, same off-the-shelf low-cost components, standard Ethernet networking, and a standard Linux operating system. So there's no special hardware involved in here. And the way we are working with MetaScale on this is that it's all part of the same farm. So you have a farm of servers. Some are running Hadoop, some are running Kognitio analytical platform, and it's fairly easy to transition servers between the two environments. So just to summarize, what the benefits of a true MPP in-memory analytical layer on top of your Hadoop cluster. Firstly, it gives you enormous speed and concurrency, which gives massive levels of query throughput. Restrictions on users can be lifted and allow them to freely interact with the data. Complexity administration effort is significantly reduced and allows for the use of a variety of existing and emerging BI analytical front-end tools, both tools that have been designed to access a relational data store and those designed to access a pre-aggregated OLAP cubes. Basically, your users continue to use the tools they've always used, but they're interacting with the data which is stored on a Hadoop system. So that basically concludes my part of this.
Thank you very much, Roger. Really appreciate it. I hope you've been able to see how Kognitio as an in-memory analytical platform fits neatly on top of Hadoop and works in the same environment. So we talked about the journey and how big data tools are here and ready for the enterprise. Now we'd like to invite you to ask any questions using the Q&A feature to the right of your screen. So we'll wait just a second for those questions to come in, and I'll pull them now. Our first question comes in. Actually, our first question is for Phil Shelley. Phil, let me give you the opportunity to just finish up and go back to your last slide to see if you wanted to add any additional thoughts, and then I'll serve up this first question to you.
No, nothing for me. I mean, just a reminder here is that Hadoop may, by some, be considered not to be ready for prime time, but it certainly is. And I saw there's some comments this week on ZDNet, and also there's an article in Harvard Business Review that included us. A lot of people are saying Hadoop now can be tamed. Well, I can actually promise you it can be tamed for the large enterprise, but it does need tools like this around it to make it usable in a normal enterprise. That's why the combination of Kognitio with Hadoop is a very powerful way to make it integrate without massive retraining of your people, especially the consumers of the data. That's the most important thing, I think, to take out of this.
Phil, thank you so much. I really appreciate it. So I'd like to thank Dr. Phil Shelley, the CEO of MetaScale, as well as Roger Gaskell, the CTO of Kognitio. We have on the screen some thank you information and some contact information. Thank you very much for attending our webinar today. The webinar will be recorded. It will be available on YouTube and some other sources afterwards. Please continue to stay connected with us at Kognitio and Phil and his team at MetaScale. You'll see the contact information on your screen now. I'd also like to bring up web briefings that we do on a regular basis, a few times a month, that are brief 20-minute versions of these kinds of presentations to give you a high-level overview. And you'll also see there a demonstration, if you go to the YouTube channel, that shows you Kognitio and MetaScale working together in a demo environment. You'll also be able to see that live and in person at the Hadoop World Conference in New York City later this month, and we expect to see a number of other pieces, some white papers and so forth coming up between Kognitio and MetaScale. So again, our thanks for taking your time and spending the energy to be with us today on the webinar. If you have any other questions, please don't hesitate to email us. Do take the time to connect with us on Twitter and Facebook and follow us on LinkedIn. Again, thank you for your time, and we appreciate your attention. Look forward to speaking to you again soon.